Okay, so the quantum bit. So as we know in classical computation, the most atomic unit of computation in the computer is a bit, right? So we have a bit which is just a 0 or a 1, right? So in contrast, the most atomic unit of computation in a quantum computer is a qubit. So here a bit is just a scalar, right? And in a quantum computer, a qubit is a vector. We'll call it psi. And that's going to be in a two-dimensional complex vector space, right? So that's just C2. So psi, right, it's a vector, so ket psi is just going to be a vector with two complex amplitudes, right? So alpha and beta are both complex numbers. And so in, well, to, be more specific, right? So if psi is equal to alpha and beta, right, this means that we have alpha times our first basis vector plus beta times our second basis vector, right? And, ket 0 is simply this vector, and ket 1 this vector, right? And so these are, what we call our computational basis states. And so if you recall what a basis for a vector space is, right, it's simply a set of linearly independent vectors that span the space. So these two vectors are obviously linearly independent. And since we have two linearly independent vectors and our space is of two dimensions, that means that these vectors automatically form a basis, since they automatically span the set. And so in a classical computer, we know that reading the state of a bit from memory is deterministic, and it won't affect the state of that bit in any way, right? But in a quantum computer, reading the state of a qubit is probabilistic and does in fact alter the state of a qubit. So these coefficients here, right, alpha and beta, these correspond to, if we square them, so the modulus square, right, is simply the probability that we measure a 0, since that's in front of the 0 ket, right? The modulus squared of beta is going to be the probability that we measure a 1. And, the modulus of any complex number, right, is literally just going to be, we know that alpha is going to be, right, just writing it in terms of its real and imaginary terms. So then the modulus of that is simply going to be the magnitude of the terms. So if we square these amplitudes, that gives us our probabilities. And so from that, we know that the modulus squared of both has to be equal to 1, right? Because these are both probabilities. This is a probability that we measure 0. This is the probability that we measure a 1. And so what this also means is that the norm of any qubit, right? So if we have some qubit psi, which is equal to, right, alpha. If we take the norm of this quantum state, this qubit, what do we get? So the norm of this vector, right, is just going to be the square root of mod square alpha plus mod square beta, right? And we know from up here that this sum has to equal 1, right? So this is just going to be equal to the square root of 1, which of course is just 1. So this is an important fact, right? The norm of any quantum state is always going to be 1. Or the norm of any qubit is going to be 1. And so, right, so ket 0, right, one of our basis vectors, it's simply going to be the quantum state which is guaranteed to return 0 with 100% probability, right? Because if we have psi, which is equal to alpha ket 0 plus beta ket 1, this simply means that these two states, right? This means that alpha is 1 and beta is 0, right? So the probability of measuring 0 is the mod square alpha, which is just 1. So 100% probability. And so, let's see here. So let's now consider this for an example. Let's consider this state. So we have this state here. So this is our alpha, right? This is our beta. So the mod square of alpha, which is equal to the mod square of beta here, is going to be what? It's going to be the mod square of 1 over square root 2 squared, which is just going to be squared, which is just going to be 1 over 2, right? So 50% probability of measuring either a 0 or a 1. So this qubit is in a perfect superposition of 0 and 1. When we measure it, we're going to measure a 0 half the time, we're going to measure a 1 half the time. And this state is canonically referred to as ket plus, just a heads up. And so now let's see how we can geometrically visualize the state of a qubit and kind of make it more intuitive. So again, we start with our default equation, right? And so we know that alpha and beta are both just complex numbers, so we're going to write them in terms of their imaginary and real terms. Okay, so we're going to sub those back in now. So we have and so notice, right, like these are rectangular coordinates, right? Now if we transform them into polar coordinates, right, which is of the form, so we would have that's a gamma, by the way. So this is in polar form, and right, so this R alpha is simply going to be the modulus of alpha, right? So just the square root of the real and imaginary terms squared. And gamma is going to be equal to the inverse tangent of B and A. This is a funny little function that's just sensitive to the quadrants of B and A, so sensitive to their signs, but it is important. And then our beta, which is just going to be c squared plus d squared, and phi, which is 2 of... Okay. Oh yeah, and these are both angles in 0 to 2 pi, not inclusive. So yeah, so now we'll go ahead and rewrite our equation again. And we'll pull out this, we'll factor out this e to the I gamma. So and then, this is phi minus gamma. Since we're factoring out a gamma, I'm just going to call this, this new little phi. So this is what we have now. And in another video, I'm going to talk more in depth about this global phase factor here. But for now, just trust the fact that this term isn't physically realizable, and so we can just drop it without any consequences. So we can eliminate this, factor out this global phase, and then drop it. So what we're left with is this congruent quantum state and so now we recall that the modulus squared alpha plus modulus squared beta is equal to 1, right? And we also know that if we introduce an angle theta in between 0 and pi, then we know that cosine squared theta over 2 plus sine squared theta over 2 is also equal to 1. Right, just move this over. And so what this means is that, this term is, well, what is this? This is the modulus of alpha is just r alpha. That's what we called it earlier, right? So r alpha squared plus r beta squared, because the modulus of alpha, right, we defined it as such. Where did I write it? Right here. And so yeah, so what we now have, so we can sub these in now too, right? So what this means is that r alpha is just the cosine theta over 2. R beta is sine theta over 2. And we're going to sub that into this equation here. So we now have is cosine theta over 2 times ket 0 plus e to the I phi sine theta over 2 ket 1. So we went from having four complex numbers, right? Because alpha and beta are complex numbers, so each one has a real part and an imaginary part, right? So we have 4 real numbers here. And we're actually able to parameterize any qubit with just 2 real numbers, phi and theta, 2 angles. And so Yeah, so theta is going to be the inclination. We now have this in spherical coordinates, right? So theta is going to be our inclination, and phi is going to be the azimuth. So let me draw this Bloch sphere here. Let me do my best. Let's say like this is our psi. So this is the inclination, theta, which again is in between 0 and pi, right? So theta determines, right, like this inclination between the north and south pole of the sphere. And then this is going to be our x-axis, this is our y-axis, this is our z-axis. So that means that then phi is going to be the distance, the angle from the x-axis here, which will tell us where our state is. And so if we upgrade to 2 qubits, it's pretty intuitive. So on a classical computer, right, with 2 qubits, or what am I saying, 2 qubits, 2 bits, we would have 2 to the 2 number of possibilities, right? Because we have 0, 0, 0, 1, 1, 0, and 1, 1. And so similarly on a quantum computer, the only difference is that we now just have 2 to the 2 basis states, which are, as you might have guessed, 0, 0, 0, 1, 1, 0, and 1, 1. And so, for example, ket 0, 1. What actually is this? Ket 0, 1. Well, this is just the tensor product of ket 0 and ket 1. So ket 0, right, is just this two-dimensional vector. Ket 1 is this two-dimensional vector. Using the definition of the tensor product, all we have now is to just expand. This will give us a 4-dimensional vector. So what we have now is 0, 1, 0, 0. Right, so that's just how tensor products work. As you might have guessed, so 0, 0 would have a 1 right here. 0, 1 has a 1 here. 1, 0 would have a 1 here, 0's everywhere else. And then 1, 1 would have a 1 here and 0's everywhere else. And so then now any quantum state in a 2-qubit quantum computer, right, or quantum system, can now be a superposition of these 4 basis states. So now if we have an arbitrary quantum state, this would now be a linear combination as, let's see, alpha 0, 0. Just like this. And again, right, if we take if we sum up, right, alpha 0, 0 squared plus alpha 1, 0 squared plus alpha 0, 1 squared plus alpha 1, 1 squared, this would again be 1 because these are probabilities, right? This is our probability of measuring 0, 0. This is our probability of measuring 1, 0. This is our probability of measuring 0, 1. And this is if we square these amplitudes, this would give us the probability of measuring 1, 1. And so now, say we now only want to measure the first qubit, right? So say we measure the first qubit, not the second. So we're only measuring the first qubit in this, super mini quantum computer. If we measure the first qubit, say we read 0. So we just read 0 from memory. So now the post-measurement quantum state would be as you might have guessed. Right, because if we measure it as 0, that eliminates the possibility that the first qubit, that eliminates like the world where the first qubit was a 1, right? So that eliminates this one and this one, or what is in the wrong order. So that eliminates those two possibilities. But these are still probabilities, right? So we have to renormalize these probabilities here because the mod squares of these amplitudes have to equal 1. So we're just going to divide by their cumulative magnitude. So we're going to divide by as so. And so an example of this would be the canonical Bell state. So the Bell state takes the form so now notice, right? Each one has an amplitude of 1 over root 2, meaning that the probability of measuring 0, 0 is going to be the modulus squared of 1 over root 2, which is also going to be the probability of measuring 1, 1, right? And that's simply 1 over 2, which is 50%. But look, if we only measure the first qubit, right, what does this do? So if we only measure the first qubit, we immediately know what the second qubit is going to be. Because if we measure a 0, the only other possible outcome is 0, right? So, more concretely, if we measure 0, then our post-measurement state would take the form right, but we have to renormalize. So and then, right, this would just cancel. You would just have ket 0, 0. Yeah, so I hope that was a helpful kind of breakdown of qubits. And I hope to see you again in a later video as I continue this introduction to quantum computing.